Some knowledge about linear programs is very helpful when studying two-player zero-sum games. If you've never encountered linear programs before, I will give you a very brief introduction in this video. A linear program is an optimization problem. We have a number of variables, say x1 to xn, and we are trying to maximize a linear function. So maximize c1 times x1, where c1 is some constant, plus c2 times x2, where c2 is some other constant, plus and so on, plus cn times xn. For convenience, we write all the constants in one vector. Say c equals c1 to cn, and all the variables we can write in a single vector as well. Say x is equal to x1 to xn. And then we can simply write this linear optimization problem as maximize over all vectors x, the expression c transposed x. So far, this is not a very interesting optimization problem. We can just make each xi very large if ci is positive, or very small if ci is negative, and that maximizes the linear function. But linear programs have also additional constraints, and these constraints are also linear. So for this we have a constraint matrix, say M, and another vector B. And then we write that we want to maximize C transpose times X, subject to M times X being less or equal than B. Subject to here just means that we can no longer choose any vector x, but only those vectors that satisfy this inequality, mx is less equal than b. The inequality may look a bit unusual at first because we have vectors rather than scalar values on the left-hand side and on the right-hand side. So the correct interpretation of this less or equal sign is that it is applied component-wise. So the first component of the vector of the left-hand side is less or equal to the first component of the vector on the right-hand side. And the second component of the vector on the left-hand side is less or equal to the second component of the vector on the right-hand side, and so on. So just kind of apply this inequality to each component separately. Finally, we also want all variables to be non-negative. So we require that x is greater or equal to the vector consisting of all zeros, right? So x1 should be at least 0, x2 should be at least 0, and so on. An optimization problem of this form, a linear objective function which we try to maximize, plus a number of linear constraints, is called a linear program. Now, here I said we want to maximize, but it could also happen that you want to minimize. So we can also have linear programs for which we want to minimize a linear objective function. Let's say the variables for such a program are y1 to ym. And in this case, the linear program looks like this. We want to minimize over all vectors y, the term b transposed times y, subject to m transpose times y being greater or equal to some vector c. And again, we want the variables to be non-negative, so we also want y to be greater or equal to the all zeros vector. You will notice that I used some symbols in both programs, the maximizing program and the minimizing program. I reused this vector b and the vector c and also the matrix M. I've done this intentionally because it turns out that if we have two linear programs like this, they are very much related to one another. One of the programs is called the primal, and the other is called the dual. We can turn the primal into the dual by first switching min and max. Second, swapping the roles of the vectors b and c. Third, transposing the constraint matrix. And fourth, switching greater or equal and less or equal in the linear constraint. If we apply these 4 changes, we get from the primal to the dual. And if we then apply them a second time, we switch back from the dual to the primal. The following theorem is the main thing you will have to know about the relationship between the primal and the dual. It's called the strong duality theorem, and it's extremely important not just for game theory, so you should really know it. If the primal or the dual has an optimal solution of finite value, then so does the other program, and the values of the optimal solutions are the same. The other thing you have to know about linear programs is that they can be solved efficiently, both in theory and in practice. There are algorithms that can find optimal solutions of linear programs relatively quickly. Okay, so this is a crash course on linear programs. This is all you need to know for the time being. There's much more to learn about linear programs, but this is all I need you to know for our purposes at this time.